Okay, this is lecture 18 for the interconnect. So now let's go to our previous lecture, lecture 17. So lecture 17 was devoted to the static power consumption, and we have learned that two major causes of the leakage current were the subthreshold current and the gate leakage current. So subthreshold current, it is reduced when we have steeper subthreshold slope. For example, let's say that this is 60 millivolt per decade. When we say this is the drain current and gate source current, then this is steep. And let's say that we have a much worse one, like 100 millivolt per decade. And happen to be, if we have the same amount of or same level of threshold voltage, let's say that this is a threshold voltage of two transistors, then what will happen to these transistors? So if you have a subthreshold slope with 60 millivolt per decade, then you will have this steep one, and so your op current will be low. However, if you have worse subthreshold slope, then eventually your op current level will be increased. So 60 millivolt per decade is the limiting factor for our op current minimization. So for given threshold voltage, we cannot further reduce the IOP level dictated by this 60 millivolt per decade rate. So we wanted to make even more steeper devices, but it is not that easy. And another one is step effect. So if we have two different transistors serially connected, and when they both of them are up and up, in this case, actually we have a certain increase of this voltage. So compared with this lower MOSFET, whose source is grounded and also substrate is grounded, so we don't have any difference between source voltage and substrate voltage. However, in this case, our body is still grounded and we have elevated temperature, elevated voltage, so we have some differences between its source and substrate. Negative voltage is applied to our substrate. In this case, we can expect increase of our transistor threshold voltage. So now this transistor becomes a transistor having higher threshold voltage. So that's the reason why we have a reduction of subthreshold current. That was related with the subthreshold current, and we have another discussion on the gate leakage current. So due to the tunneling, the gate leakage comes in, and when we had very thin oxide layer, then it becomes the showstopper. So if we have extremely thin oxide, then this is the best situation for our electron to tunnel into the gate or oxide layer. So it is extremely sensitive to the thickness. So if you have just plus minus just 1 angstrom difference, then that will make a measurable difference in your gate current level. So it is not possible to reduce oxide thickness extremely. Once you have the extremely scaled oxide layer, then you have two problems. One problem is, since this is too thin, so your gate current becomes too high. That is one thing. However, we have another problem. Yes, it is huge problem. However, most significant problem is like this. If you have small variation in your oxide thickness, then what will happen? In this case, if you have by the fluctuation of your manufacturing procedure, let's say that you have a small percentage of increased oxide thickness or small percent of decreased oxide thickness. Since it is an extremely sensitive function of the thickness, this small variation will introduce huge variation in this gate oxide current, gate tunneling current. So that makes big problem. So let me just talk about this way. If you have a relatively thick oxide, then this unit fluctuation shown here doesn't introduce much difference. However, if your oxide thickness is so thin, then the same amount of fluctuation in your oxide thickness will be a big deal. So you have much higher fluctuation of your oxide thickness. So that is not a good case. So that's the reason why using this extremely thin oxide layer should be avoided at best. So people, engineers in Intel and other company had solved this problem by introducing the high K metal gate. So here high K metal, they are two different ones. High K is not for metal. High K is for dielectric layer. So here electric layer, and for this dielectric layer we use things related with hafnium oxide, not just a pure hafnium oxide, but we have some composite layer. So for example, just at the interface between silicon and in this dielectric layer, we have just one unit layer of silicon dioxide. After that, here we have hafnium oxide. But anyway, now we have hafnium oxide high K layer, and metal gate is metal gate. Previously, it was oxide layer and polysilicon. So that was a previous gate step, but it is now changed to the metal, and this is the real standard in today's state of the art transistors. Okay. So by introducing this high K metal gate, so now gate leakage current is significantly reduced, because with much thicker hafnium oxide layer, but that is equivalent to much thinner silicon dioxide layer. In terms of what? In terms of effective oxide capacitance, because it has much higher relative permittivity and it is relatively low permittivity. So even though we have a quite a thick layer, but it is, sorry about that, the pencil is stuck, so we have to wait. Okay, so although we have thick layer, but that is so effect of a thick layer in our capacitance is compensated by the relatively high permittivity. So now we can maintain thick oxide layer or thick dielectric layer while having the reasonable value of oxide capacitance. So, so tunneling current once again is extremely sensitive to the thickness. So by increasing the thickness of this hafnium oxide layer, we can significantly reduce the gate leakage current. So that was the review of our previous lecture. And remaining topics, we have two remaining topics here. So let me just consider these ones quickly. So leakage current really depends on the input pattern. For example, here we have considered 8 different cases for our inputs. So for example, the top one is corresponding to 0, 0, 0, and the lowest one is 1, 1, 1. So depending on these cases, so for example, this voltage, the source of N1 transistor is always grounded. It's okay. However, source of our N2 device or source of our N3 device really depends on the bias condition. So, for example, let's just think about the case like A equal to 0, B equal to 0, and C equal to 1 case. Where can you find it? So A, B, 0, 0, 1. Yes, here you can find this one. So in this case, what will happen to this guy? So A and B transistors are turned off. However, C transistor, it is basically biased with VDD. So our source voltage should be increased. For example, if we have just 0 volt here, then this transistor will be just turned on. It's not possible. So in order to turn off this N3 transistor also, we must increase the voltage. So the voltage in this case will be approximately go to this level. Why? So think about this one once again. In this case, here we have a VDD, and this level becomes VDD minus VT over our N3 transistor. Then what will happen? When we have this condition, now this C transistor is also turned on. So please note that really this current really depends on the pattern, input pattern. So in order to accurately calculate the power consumption, even though in the case of static power consumption, we must consider different cases. So in order to calculate these ones, we need accurate simulation of this pattern. So not a simple manipulation, but we need more of both. The final topic in this static power consumption is power gating. So maybe you remember similar approach in the case of dynamic switching or dynamic power consumption. What was it? Previously, when we had some unused part of your chip, then for this part, you just nullify the clock signal. The clock signal is once again the heartbeat of your chip. So if you just provide no clock signal, then it does not switch accordingly. So that was the situation. However, even in this case, we can have DC power consumption. So in order to reduce this static power consumption, especially we wanted to just introduce power gating. I mean that actually VDD itself is gone. If you don't provide clock, then there will be no switching. If you don't provide VDD, then there will be no static power consumption. That is quite a simple approach. So now let's have a look at this one. In this figure 5.24, you have certain block which need to be operated. So here you have an input signal. However, let's assume that for while you don't want to use it. So although it is sometimes it is necessary, but let's say that for while you don't want to use it, then what can we do? Let's say that here we introduce certain circuitry. So here we have VDD. This is just a normal VDD, and if you just connect this VDD and this the power rail for our plug, then it will be operated in a normal way. So how can we achieve this one? Let's assume that sleep signal equal to 0. If we have sleep signal equal to 0, and here you can see that this is P MOSFET, and this P MOSFET is fully turned on and also fully turned on. They are fully turned on. Then what will happen? There will be no voltage reduction due to this P MOSFET. So you know, in this case, VDD will be just copied into this point, this virtual VDD. So you have the normal operation of your transistor. Okay, so are you with me? I mean that it's like this. You have a toy. Let's say that this is a robot toy. It is working. And how can we supply the power to this toy? So let's just say that now we have a wall, and here we have a wall, and just that is plugged in to constant, electric constant, and we just make it bond. Then there is a wire. Then what will happen? Then this toy will move, hanging around, following its own algorithm. So that is the situation shown here. Then our next goal is how can we disconnect this line? If we simply disconnect this line, then what will happen? This toy will not move any longer, and the power consumption will be just 0. So what we can do is quite simple. Apply just sleep equal to 1 or VDD. Then now our P MOSFET is turned off, and this VDD-V, so virtual VDD, is now disconnected from this VDD. So previously we had strong connection between VDD and this virtual load VDD-V. However, now when sleep is 1, then this is simply in this case, and this VDD should drive our block here, shown here, and we have many input signals. Then what will happen? So it is not possible this guy to drive this power consuming driving circuit, and eventually its value will be, the voltage value will go to 0, because there is no driving force to electromotive force to keep the voltage to VDD. So eventually it will go to 0, and the power consumption by this part will be 0. Yes, it's good. However, when we use this kind of operation, then there is no guarantee that its output values have meaningful values. Yes. So since we have applied just floating voltage to our VDD, so what will be the answer? If we have 1 or 0, does it make any sense? So it's not. So we have just a garbage value for these outputs. So when sleep equal to 1, then we should not use this output. So this output is isolated by taking this AND operation. So when sleep equal to 1, then sleep bar becomes 0, and this input, the final isolation AND gives us just 0 output everywhere. So we will not use this output. So that is the point. Yes, it sounds great. However, please note that we must turn it on and turn it off quite frequently. Then it is not that much efficient. So, previously let's use it. Then we have VDDV equal to VDD. Then let's turn it off. Then we must discharge certain power, and that is used. After that, now we have changed our mind. We wanted to wake up this block. Then what will happen? Now, when you just reduce the sleep equal to 0, then our VDD node should provide once again certain power to reactivate this power gated block. Okay, that is quite much easy to understand. So if you frequently go to sleep and go to wake up, sleep, wake up, sleep, wake up, then actually this one should spend a lot of switching power. So if that is a huge quantity, then actually the benefit from this power gating scheme will be lost. Okay. That is one thing. And of course, another consideration is we should be careful. We should be careful about sizing these transistors. If these transistors are so large, then there will be almost no voltage drop between this VDD and VDDB. However, if this is not that large enough, then there can be certain problem. So, however, if we have a too wide one, then it will also make a problem. So, sizing is also important to this header switch transistors. So, this is a matter of also design program. And now let's go to the interconnect part. So interconnect is wire, actually wire. Up to now we have considered just transistors in its intrinsic part. So let me just draw this way. However, in reality, what happens? Let me just draw a little bit further. Just a little bit here. So usually we draw in this way. But in reality, it has another end of this diffusion region. Yes, here we have diffusion region, and now we have a certain so this is in the case of n-type transistor, that will be n plus and n plus, and in the case of a PMOSFET, that will be p plus and p plus. And here we have a certain tower or metal. And here we have another tower of metal. And what we have in this case, beyond a certain level, here and there, we have certain layer of metal. And although shown in here in two-dimensional way, then it is just learning over in this way, and learning over in this way. So, for example, let's say that this is a source, this is your source, and you wanted to ground it. Then how can you actually ground this source terminal? That is simply given by this way. Here, starting from your source, intrinsic source, your signal is connected through this metal line. And this metal line is typically called as via. So this is a Latin word for taking through, mean that they are just connecting between this another level and another level of a signal. And here you have this is relatively narrow. After that you have a relatively thick line, and this thick line is learning, and eventually somewhere that is connected to the global ground of your chip. So not locally grounded, but that is learning and eventually grounded. Or, for example, let's say that not in this transistor, in the same transistor, but let's say that your drain voltage, your drain is connected to the VDD, then quite similarly, your drain is connected to somewhere, or let's say that this is now source of your P MOSFET, then that is connected to your VDD eventually. So please note that ground or VDD is not that much easily available in your chip. In your chip, you have only some places to provide these powers. Then that power should be distributed to everywhere inside your chip, and that is done by your metal line here. Then of course, this is just one metal line, and you must route them then in order to make a certain chip. Then you must introduce another level. Let's say that this is M1. Then you have to another level of a signal M2, and also you can introduce even higher level corresponding M3, like that. So you can introduce multiple levels of metal line. They are used to connect your transistors. So compared with these transistors, so do you remember the size of these transistors? So please note that previously we have thought about the distance between here and that. This is just corresponding to just several hundred nanometer scale. And how big is it? This is just nanometer scale, and here we have a metal, and even in this metal case, the size is just orders of several hundred micro, not micro, nanometer scale. So they are all in the scale of point something micrometer scale. However, when you have a look at these M1, M2, and even higher number of metal lines, the size is no longer in small nanometer size, but this is close to the micrometer size. So that is the situation. So now let's think about this one. Here you are looking at two parallelly running two wires. What is it? Actually, this is corresponding to your metal lines shown here. So, of course, depending on level M1, M2, M3, then the size of a metal line can be differed. For example, let's say that let's talk about the specification to describe wire geometry. So we have some numbers or some quantities called as pitch in many cases. So even even in our transistor, we have something like called as pitch. So let me just first consider this CPP concept. So let's say that this is your transistor, and the most critical design variable corresponding to, or technological variable corresponding to the size of your transistor is CPP. So it is given by this difference. Here you have the sphere, and it is when you have a look at it from the top. So when you have a look at it from the top, then how does it look like? It will just draw in this way. You know, this is corresponding to, so sorry about that. Here, if we have a look at the transistor from the top side, then this part and this part will be just drawn as a single rectangle. Yes, this is called as diffusion. Then when you draw your gate, gate poly, then it becomes, this part becomes this part. Yes, now you have your gate. But anyway, here you have via, and it is written in usually in this way. This is also another via. So actually we can consider the distance between these two contacts. So the minimum size of you can achieve for a given technology. This is important to consider the minimum size of your transistor. Okay, so if this size is small, then it means that in this, using this technology, you can make a smaller device. If this value is larger, then actually you must spend more silicon area to realize your single transistor. So that is called as CPP, and that is called as contact poly pitch. So the term pitch in this field just to specify the size of something. So distance between something, which is important. So in this case, we can consider also pitch in the case of wire. This is wire, and this is intrinsic transistor, but everything in this field can have a certain pitch. So let's just define this one. Here we have one line, then maybe I would like to say this distance, the midpoint of this point, this one line, and midpoint of this another running wire. I wanted to just measure the distance. So that is the pitch. And here we have half of width, and here we have half of width, because my starting point and ending point is just the midpoint of each wire. So you can easily understand the distance between these two wires is simply given by the spacing between these two wires and half of width, So therefore full width, that will be the value of pitch between two wires. Okay, so are you with me? This is not that difficult to understand. And also as we can define aspect ratio. Aspect ratio is just the ratio between this height and width. So this is width and this is height, called as thickness here. So this ratio T over W is defined as aspect ratio. So maybe you have, since you are all interested with semiconductor devices, maybe you have heard about this one. So we can think about certain skyscrapers. So where can you find it? If you go to metropolis area, then you can find many of these kind of things. So what is the aspect ratio? Here we have a relatively narrow area and it is quite tall. So we can think that this aspect ratio is quite high. But instead of that, think about the houses in rural area. Then how does it look like? It is like this. So it has a relatively wider space compared with its height. Which one has high aspect ratio and which one has low aspect ratio? Certainly this guy has high aspect ratio and this guy will have low aspect ratio. So let me just ask you once again the same question. In this metal line wire, if we increase aspect ratio, what will happen? Then it is corresponding to this tall wire. And if you have a low aspect ratio, then it is corresponding to relatively short wire. And the aspect ratio becomes higher and higher. And it is because there is the reason. So you can see that all the processes had aspect ratio is not that high, but nowadays it is becoming larger and larger. Why? I wanted to tell you the reason. So now let's think about the signal propagation between these two lines. Okay, here we have a certain signal, and here we wanted to get the signal. Then when the signal propagate, there will be the voltage reduction because that is given as the form of voltage and current. So eventually we have to have a certain decrease here. So the best way to have small loss due to this metal line, that is quite easy. If we have a relatively low resistance, then we will have a low loss due to this metal line. It is quite simple. So low resistance is important. Then how can you reduce the resistance of this metal line? It is simple. You have one point and another point, and you want to reduce the resistance. How can you do that? One way is just, of course, one way is just to make it short. Then there will be a small resistance, but it is none of our concern because we are now talking about the unit length scale. So for a unit length, how can we reduce the resistance? So then let's say that L is kept as a constant. Then the remaining way to increase or decrease the resistance is just to increase the width or area of these two surfaces. So for example, if you can make it wider, then you can reduce resistance. Another way, if you make it taller, then of course you can reduce the resistance. Good. However, which way is more preferred to your scale device? That is my question. If you have this wide one, it's good, equally good. But point is, now you are consuming more silicon area to send a signal. It means that, we are doing our best to minimize the size of transistors. Why? Because we wanted to integrate as many as signal processing unit into small area. But although transistor part, they are doing their best, but if we just allow this kind of wide wire as its minimum size, then it is just showing that we are just losing the game in terms of metal line. So we don't like spending more area in this same metal line. So in order to keep the resistance in a reasonable value, reasonable level, while scaling the size, then this is one way we can do. Make it tall. Then with the same size, same area, we can introduce higher conductivity, means that lower and lower resistance. Okay, are you with me? So this is the way we can say, and this is just showing our um, previous technology, not our but Intel's previous technologies. So please have a look at these ones, 40 nanometer and 45 nanometer and 19 nanometer technology. So you can see that in the case of a 19 nano technology, we had 6 metal lines, and now in the case of 45, we have more metal lines because our circuit becomes more and more complicated. So the fab guys technology should provide more and more metal lines to make it routing easier. So then my question is, where do you have transistors? Can you find transistor in this slide? Yes, so please have a look at this. This is your transistor. So you may find that actually, although we have thought about the transistor several times, but in reality, in its size, it is not that large. So compared with this other metal lines, it is quite a small part. Of course, size is not the only story. All kinds of important signal processing is done here, so it is important. It really determines the signal, but at least in the size, in terms of size, transistor is not a big portion of our wall. Okay, so you know that this is a source of drain and source of drain, and here you have a gate, and gate is running of course in this way, in this vertical way. And what is it? This is called as via, and this is also via. There are via. So between metal and metal we have many vias. So simply speaking, in this point, is directly connected to this M1, M2, 3, and 4. What happens to this guy? Eventually, it is going to the top level, and this top level, maybe this one will be connected to your ground or VDD. It is used to set the bias voltage. On the other hand, for example, let's have a look at it. This one, what will happen? This one goes and ends here. What happens? Actually, although not shown in this two-dimensional cut, but this metal one line is running in this vertically to our computer screen or TV screen. So, and it is routed somewhere. So we can make some signal processing using this line. Okay, so that is uh, the one. So since we have many different metal lines, so we can make a complicated signal processing. And when you go to 45 nanometer technology, the situation becomes more complicated. Yes, now we have more and more lines. And where can you find transistors? Yes, still you can find transistors, but I'm not quite sure I can point it correctly. So where we have, okay, somewhere here we have a small transistors, and it is not that much visible in this case. So we have many metal lines. And point is, let me just consider one thing. Let's say here we have a certain lines, metal 2 level. So everybody understand this line is not just isolated and it is running vertically. Of course, it has its neighbor here. Also, it has a neighbor here and top neighbor and also bottom layer, bottom neighbors. So please think about the set of running lines vertically, and they are closely packed. So this is our spacing and this is our spacing. So we have some differences, and now this case can be regarded as metal, and they are separated by certain number distance s. Then what will happen? If this is metal and this is metal, then we can treat it as what? Resistor? No, because this is dielectric material. So this is not resistor, but it can be also considered as a capacitor. Point is, it is surrounded by its neighbors. Not only this right one, but it has the left one, and also it has lower level and upper level neighbors. So all of them will contribute to certain capacitances to this central metal line. So when we consider this metal line, we must consider two things. Two things is that previously, when it comes to this one, we have thought about reducing the capacitance or reducing the resistance. So that's the reason why we have increased its aspect ratio. Yes, that was it. So we must consider this metal line as a resistor. That's true. But at the same time, if we have taller and taller lines, then also what will happen? If we have taller and taller lines, then here, although the space is the same, spacing is the same, but their faces looking at each other is now increased So what you can expect is if you introduce narrowly, closely packed two parallel wires, and if you increase the height of these wires, then you can eventually increase the capacitance of your transistor or your wires. So simply speaking, by increasing the height of your metal line, you can eventually reduce the resistance per unit length. However, also at the same time, you can increase the capacitance. Of course, what you can expect is important one is the RC product, because you wanted to send signal, and if you have resistance and capacitance, then that will make a certain RC delay unit. So you wanted to actually reduce the total product between R and C. Okay. So, and please have a look at also this one. And what is this? Low K. What is meaning of low K here? It is saying that this relatively dark region here, there, you may find so many dark regions. So relatively bright ones are corresponding to your metal, and in between there is a dark region. So this is a material having relatively low permittivity. Why do we have introduced low K material here? It is because we wanted to reduce the capacitance. Once again, capacitance is given by the permittivity, area, and the distance. In this case, we have introduced the low K material to reduce the capacitance. This is quite much in the opposite the case of our oxide layer. In our oxide layer, we wanted to maximize the capacitance, so we introduced high K materials. In the case of a metal wire, we wanted to reduce the capacitance, so that's the reason why we have introduced low K material. Then, before going into our main discussion, I wanted to introduce the slide, the third slide of our introduction. So I think that this is nowadays the hottest topic in the VLSI. So in these days, so we have two major international conferences on the semiconductor devices. One is called as IEDM, and one is VLSI technology. So IEDM is annually held in December, and VLSI in June. So they are just separating 1 year. And here in our VLSI in this year, June, Intel has provided this slide. So I just took it from their presentation material. And this is their newest technology. Well, although we have many different versions, but point is quite simple. Please have a look at this, this one. Backside. Backside means that here we have wafer usually, and usually silicon wafer usually having the size of around 600 micrometer, not nanometer, but 600 micrometer. So in the realistic scale, where can you find your transistors? Your transistor cannot be visible because that is located on the surface of your wafer. That was the situation, and on top of it, so we must provide our signals. So please have a look at this graphs or this figure once again. In this case, this one is corresponding to your signal. It is time varying and it can be either 1 or 0. So this is really time varying. And please have a look at this way. What is it? Its value is either 0 or VDD. It is just connected to a voltage source. So simply speaking, from the viewpoint of our silicon wafer, let's say that this is the interface between your silicon and upper metal lines. Then what you do is, using this so-called front side of your wafer, you provide both capability. One is power and one is signal. These two quantities, of course, power and signal, both of them are just voltages. Yes. However, point is signal, it is dynamically changing, and this one is just statically given. So 0 or VDD. However, both of them is provided in this way. So the consequence of this situation is front side is actually very much populated and heavily occupied by busy lines. Metal lines are so busy. So the point of this backside power delivery network is that, okay, we are now just wasting this backside. Then why don't we just assign our power delivery capability all to the backside and leaving only signal processing to the front side. If backside and front side share the role, share the task, then we can reduce the burden loaded to the front side. Then when the front side has more room to do something, then what we can do is we can relax the scaling pressure. Okay, so that is the main motivation of our backside delivery network. Well, is it realized or not? As of November 2023, we don't have the mass production of this backside power delivery network, but we are expecting soon we will have this capability. So very soon. So now let's have a look at it. Here we have the level of our transistors. Here we have transistors, and now the power, which has a relatively larger size, is provided from this back side, and instead of that, here front side is only reserved for signal lines. So now you can increase the distance between your signal lines considerably. That makes your life much easier. So when you are, as an engineer, if your life become easier, it means that the rate of failure, chance to failure of mass production can be significantly reduced. That is the point. Okay. So in order to achieve this goal, there are many things to be required. So you wanted to send your signal from the bottom. Oh yes, I have here VDD. Then I will just feed my VDD to this small transistor shown here. This pretty one. Then how can you do that? We should learn 6 100 micrometer and provide a signal. Wow, that is not a clever idea because since the distance is quite long, close to 600 micrometer is just 0.6 millimeter, which is huge distance. So it is not a reasonable way. So in order to achieve this kind of backside power delivery network, eventually we must make it thin our substrate so that it becomes quite thin. Yes. After that, we can introduce certain VDD. Then it is provided in this way. So depending on various versions, so starting from this VDD, so one is starting from in this back side, but eventually go to front side and feed into our transistor. That is one version, and Intel is now advertising that their new idea, they can just provide the signal not going into the top but just side from the its transistor side. It can provide the power to our transistors, whatever. So anyway, following this way, we will have more room to release the scaling pressure for this how can I say this scale device, most state-of-the-art devices. So that is one of the hot, I think that actually the single most hottest topics in VLSI in these days. So using this one, they can reduce the size of chip even further. Okay, so there are so many clever guys in this community. So they are doing amazing jobs every year. So yes, so we can expect that still we have more rooms to the progress. Okay, so now let's go to the main contents. Simply, this 6.2 tells us that we must consider the interconnect as a combination of resistance and capacitance. So I have already discussed this concept in this point. When we have two parallelly running metal wires, and we have to consider these things. What is the resistance between this point and that point? That is the resistance. And during that unit length, how much it is electrically coupled with neighboring wire. These two things are needed. So then we can just think that, okay, there is a resistance and there is a capacitance for unit length. If this length is quite short, then these two metal lines, so from the viewpoint of this central one, can be realized or modeled in this way: resistance and capacitance. Here we have one terminal and another terminal. When you have one terminal, the other terminal. If we have A and B point, okay, is not very well working. So here, if we have A and B point, then we can say this is A point and this is B point, and we have a resistance and capacitance. Of course, let's say that if this metal wire is, or the neighboring metal wire is placed far away from the central one, then what will happen? The resistance will not be changed any longer, but instead of that, the capacitance is expected to become much smaller, because this capacitance is given by the distance between two metal wires. Are you with me? So if we have, instead of that, if we have a closely placed metal wires, then we can expect the capacitance will be increased significantly. Actually, inversely proportional to the spacing between these two metal wires. And please note that since we are working with this kind of view, then between A and B, when you increase your A voltage VA from 0 to VDD immediately, then there will be certain delay to have also VDD signal. So what you can expect is here we have a RC delay, and maybe you remember that you have already calculate this kind of thing. So this is more or less corresponding to RC delay. So although the input signal is abruptly increased, but the response of your signal will be just delayed by RC delay time. So in order to reduce the delay due to wire, you must have a reasonable value of RNC. And everybody in this community says in this way. In previously, wires were not that important. At that time, transistor was the trouble guy because the performance of a transistor was not that high, and at the time, metal wires were so wide. So there were two guys, one transistor and metal, but this guy makes every day some trouble, and this guy doing quite well. So all the technologies, everybody just concentrated on this guy. How can we improve the behavior of this guy? But now time has passed, and this guy, its performance has improved quite a lot, and it has many knobs to increase its performance, because main focus was the transistor. And now we have the problem for interconnect. Why? We wanted to reduce the size of transistors significantly, so now at the same time the size for our metal wire is also rapidly decreasing. However, although transistor has many knobs to improve its performance, many innovative ways to improve its performance, but how can you improve your metal wire? This is just a wire. Then how can you reduce the resistance and reduce the capacitance, whatever, if you have just a metal line? So it becomes more and more important. In nowadays people have some agreement. Nowadays transistor is already good. The troublesome guy is now interconnect. Modeling and improvement of interconnect is really eagerly needed, and placing some things to minimize the wire delay is becoming more and more important. That is the situation. So now let's come back. Simply speaking, when you consider an interconnect, then what you have to do is just to find out this number. Per unit length, what is the resistance? Per unit length, what is the capacitance? Once you know these parameters, then if you have a long line of your metal wire, then you can just make it as, or consider it as, a distributed circuit. So then the propagation over this distributed RC network is quite easy to consider. You can do it quite well. So now we must consider how can you reduce resistance and how can we reduce the capacitance. The resistance first and capacitance rest will be discussed in this course. Okay. Do you have any question? Yes. So maybe if you have attended the electromagnetic course given by the ECS curriculum, you remember that actually this kind of RC modeling or RLC modeling is the typical way we do to model any kind of signal transmitting structures. So this is the typical way we do in the case of electromagnetics. However, from the viewpoint of frequency, usually our operational frequency limited to certain gigahertz level in the case of our conventional logic system, then this gigahertz range is too low frequency to consider meaningful inductance consideration. So usually instead of considering this inductance first, we just consider R and C. If we go to more higher frequency, then we must consider inductance component also. So now let's go to wire resistance. Wire resistance from the viewpoint of designers. So think about you are a designer. Then what you can do is just to draw a rectangle. You have a source of your signal and you have a destination of your signal. Then what you can do is just to connect them. Then let's say that if you connect it in this way, or if you connect these two source and destination in this way, it's your choice. You can make how wide is my wire or how long is my wire. Okay, that is your design considerable. However, the thing you cannot change is somewhere here. So let's say that this is the length of your wire and this is width of your wire, and here you have length of your wire and width of your wire. As a designer, you can change it, but what you cannot change it is this thickness. You cannot come to your fab guys and say that, okay, I want to have more thicker wire. Please, for me, increase the thickness twice. That is not negotiable. So this is just given by your given fab. So as a designer, you wanted to make a quick way to estimate your resistance, not bothered by this technology involved one. Only having length and width, you wanted to estimate the resistance. This is provided by this sheet resistance. So simply speaking, its idea is quite simple. Let's say that this is unit length and this is unit width. If you increase your length twice while keeping the width, then what will happen? Then you will have just twice larger resistance. That is quite easy. While keeping the length equal to 1, unit 1, if you increase your width twice, then what will happen? You will have just half width. So although you don't know what is the exact value of your resistance, but you know that your wire resistance is simply given by proportional to the length and inversely proportional to the width. That's it. So then, of course, we must have the coefficient. And what will be the coefficient? The easiest way is just to introduce unit length and unit width. then you will have a certain amount of resistance measured. That measured quantity is given as sheet resistance, and the sheet resistance has the, usually we introduce this square, although I wanted to draw square. However, in my PowerPoint file I could not draw the exact square, so instead of that I just used this slightly wider rectangle. But usually people use real square to represent this sheet resistance. This sheet resistance times L over W, that can give us the uh, this resistance of a wire. Let's have a look at this one. If you have a wire, its length is 1 micrometer and its width is like a 0.125 micrometer, like this. Then in terms of your sheet resistance, what is the resistance of this wire? Obviously, this is just 8 squares serially connected, so you will have just number 8. Are you with me? So it is quite much intuitive. When you have a look at certain layout, then you can just see the ratio between length and width, then that will give you the estimation about your resistance. So simply speaking, if you have 1-to-1 wire, then its resistance is equal to 2-to-2 wire. If you have 2-2, then the resistance will be the same as this 1-to-1 case. So this is shown in your figure 6.6, and when you have a look at it, if we measure the resistance between this and that, and resistance between this and that, you will find, although their sizes are quite much different, but their resistance will be the same, because width is becoming twice and also length is becoming twice. Okay, since time is up, I have to stop here, and we will continue the discussion about interconnect on next Tuesday. Thank you for your attention.